And greetings to my 4 or 5 subscribers who are somewhat intrigued by science because they are somewhat inclined to disprove Al Gore's theories about carbon dioxide warming the planet. I'd like to explain my theory. This would give me more clicks, this would give me less. In a similar fashion, if you put a type of a Geiger counter in space, it will receive more clicks than that same Geiger counter on the ground, which might lead you to assume that the source of your radiation is out there. And it so happens that if you get away from the Earth, further out into space, away from the Earth's magnetic field, radiation is more intense. You might want to know this if you're planning on going into space on a long mission. If you want to go to Mars, you would like to know, is the radiation going to be a problem? And you might want to know, are there periodic increases in radiation that might disturb your instruments on your spacecraft and might impact your health? Just as the Earth has a magnetic field, the Sun produces a magnetic field, and it extends far out into space beyond all the planets. It's a magnetic field filled with subatomic particles from the Sun. But space is constantly radiating from all directions cosmic radiation. The heliosphere deflects some of this cosmic radiation, which happens to emanate from novas all throughout the galaxy. Stars are exploding and creating subatomic particles that stream outward from that star at the speed of light, and they're everywhere. The galaxy is huge, and so there's always this background radiation emanating from novas, and it's more or less constant as it strikes the Earth's atmosphere. And it hits the molecules of gas in the Earth's atmosphere, the nitrogen, oxygen, for example. And these little speeding subatomic particles can actually bust a molecule of oxygen and create an unstable radioactive isotope. When they date fossils, they measure the amount of carbon-14, a radioactive isotope. There are other radioactive isotopes. I suppose most any element can be rendered unstable by an impact with a speeding subatomic particle. That much you can understand. I theorize that the Earth is in motion around the Sun is in motion around the galaxy, and perhaps in motion around another star. But nevertheless, it's moving, and NASA has recently determined that the Sun is moving in a certain direction at a speed of about 50,000 miles an hour. If it should encounter some hydrogen gas, the remnant of a star that exploded in the past, this hydrogen gas would impact the Sun, in my opinion, and the Sun's gravity would suck it in like a vacuum cleaner, as I've illustrated here. The density of this gas varies. When there's more of this gas, I theorize that the cosmic radiation is lower because the cosmic radiation is deflected, moderated, scattered by this gas because it's impacting the molecules of gas. When the density of this gas decreases, more cosmic radiation would strike the Earth's surface. When there's more gas, there's less radiation. When there's less gas, there's more radiation. I prepared a chart here, very simple, showing the relationship between this gas density and galactic cosmic radiation count, GCR count. We can measure that with an instrument that works in a similar fashion to a Geiger counter. And there's one of these fast particle detectors on board the space station, the International Space Station. And scientists have these things in various locations on the Earth. These particles are traveling so fast they penetrate metal. And as they do so, they actually impact the individual molecules of the metal and cause subsequent radiation. But this gas moderates the incoming cosmic radiation depending on its density. So when the gas density is high, GCR count is low. And when the gas density is low, GCR count is just the opposite, it's higher. If this gas is sucked into the sun like a vacuum cleaner, it would affect the total solar irradiance, according to my theory. So that when the gas density is high, GCR count being low, the total solar irradiance would increase. And when the gas density becomes low, GCR count would become high, and the total solar irradiance would become low. So you have a variation in the sun's output, and you have a variation in the GCR count as measured at the Earth. And this GCR count affects the creation of radioactive isotopes, such as beryllium-10, for example. When GCR count is low, the creation of beryllium isotopes is low. And when the GCR count is high, there are more beryllium isotopes created. These 3 or 4 factors correspond in this fashion. Now, if you think about the climate of the Earth and focus on the polar ice caps, you could imagine that when the gas density is high, the GCR count would be low, the total solar irradiance would be high, and the polar ice would be melting. When the gas density is low, the total solar irradiance would be low, and the polar ice would be freezing. And you can measure this in the past by checking the production of beryllium-10. You could tell what the gas density was in the past by comparing it to the level of beryllium-10 preserved in ocean bottom sediments and in ice cores. So therefore, my point is, if my theory is correct, the brightness of the sun can be detected in the past by the archived beryllium-10 buried deep in the snow, layer upon layer, preserving it over a sequence of time. And if the measurement of beryllium-10 shows that it corresponds in this fashion. The glaciation and interglaciation of the Earth's poles, the ice on the poles, the ice caps growing and melting. This would pretty much clinch my theory that the presence or absence or density of interstellar gas determines our climate. Until recently, NASA said that this gas does not enter the solar system. It is repelled by the heliosphere, this electromagnetic barrier. Well, they've decided, well, that's wrong, and it does get in. So I've made a series of videos lately trying to explain this, and it's not complicated. If you can understand a Geiger counter, and if you can understand ice melting, if you can understand sunshine striking the Earth's surface, if you understand that the solar constant measured in watts per square meter at the Earth's surface perpendicular to the sun, if you understand that that solar constant is not constant, that it varies and has varied over time, it's relatively constant from day to day. But going back 10,000 years, I would fully expect that the watts per square meter to be vastly different than what you find today.